Hello everyone, welcome to this introduction of our work, Paint Transformer, Feed-Forward Neural Painting with Stroke Prediction. As shown in these examples, neural painting refers to the procedure of producing a series of strokes for a given image and non-photorealistically recreate it. Typically, there are two major components in this task. The first one is stroke predictor to generate parameterized strokes given a target image. In neural painting, neural networks are widely used as the generator. The second one is stroke renderer to paint the produced strokes on a canvas to render the painting results. To enable the training of neural painting pipeline, the stroke renderer should be differentiable for optimization. In the literature, we can mainly divide existing methods into two categories. On the one hand, some works view neural painting as a sequential decision-making problem and use reinforcement learning to solve it. Once trained, strokes can be generated by the RL agent in one feed-forward pass, so the inference efficiency is satisfactory. However, in reinforcement learning, it is not easy to train a stable RL agent. On the other hand, there are also some works searching for a set of stroke parameters iteratively in a large search space. Such optimization process does not need training for a stroke predictor, but the time-consuming optimization significantly limits their application in practice. Different from this method, in this paper, we view the problem of neural painting from a new perspective, which is stroke set prediction. Under such setting, the training can be more efficient, which takes less than 4 hours on a single GPU. And in the inference time, we can obtain the final painting in near real time under the resolution of 512. The contribution of this paper can be summarized as follows. First, we formulate neural painting as a set prediction problem, where parameters of a set of strokes are generated in parallel. Interestingly, object detection is also a typical set prediction problem, and we can build a bridge between these two tasks. Then, inspired by recent object detector DETR, we consider strokes as rotated objects and propose a novel transformer-based stroke predictor. Different from object detection, no labeled training data is available for stroke predictor. To address this issue, we propose to use randomly synthesized data. Experiments demonstrate that the model has great generalization ability on real-world images. We start the introduction of our method from stroke definition and design of stroke renderer. In this paper, we mainly consider rectangular stroke, which can be defined by center coordinate of the stroke, rotation angle, height and width, and stroke color. Under such definition, we conduct a fine transformation on a primitive brush based on shape parameters to warp the primitive brush towards the correct position and colorize it. Therefore, our stroke renderer is a parameter-free module without the necessity of training. Meanwhile, the affine transformation is also differentiable as we expect. Our stroke predictor takes two images as input. One is the current canvas IC, and the other is the target image IT. It predicts a set of strokes which can cover the difference between IC and IT. Inspired by DETR, we propose a transformer-based architecture. IC and IT are encoded by convolutional networks and transformer encoder firstly. Then, several stroke queries are set to transformer decoder, and the decoder output parameters of a set of strokes and their corresponding decision scores. Only strokes with positive decision scores are painted on the canvas. Given the design of our stroke predictor, the core problem is how to train it without annotated dataset as the case in object detection problem. In this paper, we propose a novel self-training framework based on randomly generated strokes. First, we randomly sample a foreground stroke set and a background stroke set, and generate a canvas image based on the background strokes, and a target image based on the canvas and foreground strokes. Then, Stroke Predictor tries to predict parameters of the foreground stroke set. The stroke renderer paints the generated strokes on the canvas image to obtain the predicted image. In this way, the optimization can be conducted on both pixel level and stroke level by checking the consistency between target image and predicted image, and comparing the foreground stroke parameters and the predicted parameters respectively. The objective on the image level is simple, and we use pixel-wise L1 loss to encourage the consistency between the predicted and target images. On stroke level, we firstly propose some metrics to measure distance between two strokes, which include parameter-wise L1 distance, W distance from a recent work in rotational object detection, and binary cross entropy to measure the decision score similarity. More details on the formulation can be found in the paper. With this matrix, similar to DETR, we find the optimal permutations of generated strokes and target strokes using Hungarian algorithm, which produces minimal total strokes distance. Note that, although in neural painting, stroke order is an important issue, we set the objective of learning stroke order to the image level, and on stroke level, loss is computed under the optimal permutations. In the inference time, we design a Coarse-to-Fine inference pipeline as shown in the right side. The inference is conducted on several Coarse-to-Fine scales. Painting on each scale is dependent on results of the previous scale. In each scale, several non-overlapped patches would be processed independently in parallel, and the result of each scale is derived by combining those patches together. There is an example of painting on 5 scales. In qualitative comparisons, we provide our results by painting on 2 different numbers of scales, result by optimization baseline and by RL baseline. From these results, we can observe that compared with optimization baseline, our method produces finer painting results in those texture-rich areas and produces fewer and bigger strokes in those texture-less areas, as a human painter would do. Compared with RL baseline, we can generate more vivid results with clear brushes and proper artistic abstraction. The quantitative results on the left side also supports the observation in the previous slide. In the efficiency analysis on the right side, our method enjoys the best inference and training efficiency. The inference is slightly faster than RL baseline and significantly faster than optimization baseline. The training takes less than 4 hours, which is more efficient than both baselines in terms of total training time. Moreover, our method does not require users to provide training images. Such data-free manner makes it even more convenient. Here are some animated results. Here are some more interesting extensions. For example, we can change the primitive brushes with other shapes or textures without retraining the stroke predictor. Combining with neural style transfer, we can also achieve stylized painting. In conclusion, Paint Transformer reformulates the neural painting problem from a set prediction perspective and predicts a set of strokes in a feed-forward way. A self-training pipeline based on synthesized data is proposed to train the stroke predictor, which demonstrates excellent generalization ability on real-world images. Experiments demonstrate that Paint Transformer can generate paintings with better trade-off between artistic abstraction and realism, and achieve high training and inference efficiency at the same time. Code and model are available to public. If you have any question, please do not hesitate to contact us.